All right, well, anyway, for industrial Ethernet. All right, so for those standards. Anyway, the 10 is 10 megabit, the 100 is 100 meg, the 1000 is 1000 meg. Base stands for baseband. Remember, if you guys remember, we had baseband and broadband, so we had those two slight differences. And then the 2 here is defining overall our cable type, our communications kind of system. In this case, it's thin wire coax. All right. If you don't remember what coax is, it's what we are using to actually connect basically your modem to the internet. All right. Remember, that is an analog-based communication system, and we normally use it based on frequency. So if we think about our coax, we've got our outside sheath. You've got a little itty-bitty conductor right in the center. We've got some separation of some sort to protect that, some insulation. And then on top of that insulation, we've got our braided copper mesh. And that's what's providing grounding and interference and things like that. So keeping interference from happening. Not providing interference, keeping interference happening. Light difference there. All right. So that's coax in the long run. So that one's thin wire. That is 6.3 millimeters, or about 1/4 of an inch in diameter. All right. The 10 base 5, that is thick wire. That is 13 millimeter, or 1/2 an inch diameter. But otherwise, they're both still just coax. Larger the coax, we normally can provide better interference reduction because we have more space, more shielding. So it's, bigger the better, right? Isn't that what they always say? The bigger it is, the better it is. Not necessarily actually true, but that's kind of what people say. 10 base T, on the other hand, so 2 and 5 are both coax. T is unscreened twisted pair cable, which is 0.4 to 0.6 millimeter conductor diameter. So 10 base T is also going to be a hub-based topology, right? Where the 10 base 5, that was bus. And if you remember, bus was, you've got one line and everything kind of connects to it. And then our hub was more like a circle with all of our devices hanging out on it. All right. And then 10 base F, this is optical fiber. All right, so this is still only 10 megabits per second. Our fiber optics nowadays are way beyond that. They're way beyond 1,000 base. All right. But it's still fiber optics. And this was a point-to-point, so this is just one device to another. We're not linking things. It's one-to-one. Once we get into that 100 base, so that's again 100 megabits. The TX is going to be copper. The FX is going to be fiber optic. 10 base T4. This is designed to operate at 100 megs over 4 pairs of Cat3 cable, but this option never really gained widespread acceptance. It wasn't used very often. The 10 base T2 never really also wasn't ever really implemented. This is supposed to operate over just 2 pairs of Cat3 cable. Never really used. So the 2 ones in this were really the top 2, the 100 base TX and the 100 base FX. We get to the 100 base X, or the 1000 base. Again, this is gigabit. So SX is your short wavelength fiber version. LX is your long wavelength fiber version. And CX is a short copper cable based on the fiber channel standard. All right. Last class we did talk about there was that little device. It was kind of looked like just like this. It had like that funky big hunking thing hanging out the top of it. All right, and I told you guys that was that fiber optic to electrical, or electrical to fiber optic conversion. So you can, if your devices are close enough and you need that super high speed, you can run copper between them. You don't have to technically run fiber optic there. We just normally run fiber optic over long distance. If you're doing really short runs, under like 10 feet or something, you can just do a copper over that super high speed network topologies. So just something to think about. All right, so the early days of Ethernet. And here you can see one of those coax connectors. Actually, you can see 2. We've got the one on the front and the one on the back. This one on the front, I think this is probably like a PL239 or something like that. All right, and we really like coax connectors for anything dealing with frequency. Again, that analog world. They do a great job of providing a connection from wire to wire, wire to connector, whatever it is, while still maintaining that grounding on the outside for protection purposes. The shielding is still there. So it's really good for that analog world of RF signals. That's why we like the coax cable, those screw-on connectors. But anyway, early Ethernet was primarily developed for the office type environment. So you had an office that you all wanted to share a printer or documents or whatever the case was. It was designed for that purpose. Not really designed for the home because you didn't really have that big of a need back in the early days of transferring that much information in. But obviously in office environments and business environments, it's like, yeah, we all need access to printers and shared folders and things like that. So instead of buying everyone their own printer, we just shared. Right? Yeah, and we have rapid advances over the years. I mean, you can see where we came from. I mean, I never did a coax network myself. I saw all the parts and pieces, but I've never actually wired one. But now we're at Ethernet with gigabit, 2.5 gig, 5 gig, 10 gig, depending on your motherboard that you have and the networking cable that you have in your house. Or you could be running fiber optic right off your desktop. Right? There are very few people I know, actually, I don't know personally anybody who truly needs fiber optics coming from their desktop to something. Okay? Unless you are like a YouTuber, dealing with massive amounts of large video files or maybe even CAD files, but and accessing those from another computer. Why would you want to do that? Well, that way all your files are stored not on your local machine, but on a server, which makes accessing easier from multiple different places. But unless you're doing that type of work, you don't really have no need for a home person to have that type of network. 1,000 meg at home, plenty fast enough for you. Yep. RJ8 coax cable was like the go-to, and this is, as I said, quite impervious to the electrostatic interference, so it helps with any interference. 8X, it's RG8 back then. We still have RG8X nowadays. A younger sibling, I'm going to call to that, would be the RG58, I believe it is. So a little bit of give and take going on there. Coax sucks because there's like hundreds of different versions of it. You've got the RG58, the RG8X, you've got the PL this, you've got the Flex. What am I? Are you freaking kidding me? RG6. RG6 is what most of the coax in your house is. For your TV signals, if you have coax in your house, most likely it's RG6. Unluckily, coaxes also have different impedances. So like RG6 is 75 ohm impedance, where RG8 or 58 is 50 ohm. And the impedance does matter in the long run. Screws with things. You gotta be freaking kidding me. So that is just, an absolute pain in the rear end, if you ask me. So again, just kind of something to keep in the back of your mind. Oh, this is, I call this a PL connector. It's also the N-type connector. This is a pretty freaking rugged connector. It is screw-based, as you can see. There are threads on the inside of this thing. And normally this whole section actually kind of slides forward and backwards a little bit on the connector, which is nice because you can actually like insert it and then just screw the connector around the outside. You don't have to screw and twist one of the cables as you're screwing it in, so that the screw portion is actually kind of floating a little bit. So connecting things with it is really nice. Not like the TV connectors where you're trying to undo that little nut. It's just like a freaking pain in the butt, and half the time you end up spinning the cable with it because it's just so tight and frustrating. This is like much nicer of a connection to use. If this is what I think it is. So yeah. All right. So modern industrial Ethernet. So based on 10 base T or 100 base X, either way. We are using the RG45 connection, which is what you guys are seeing right there. As you guys know, this is the pass-through type, so the wires are sticking out the end. All right. And once we have the right crimping tool and you crimp that, it just cuts all those ends off, which, remember, makes your life so much easier. All right. As I said, if you can get your boss to buy the good stuff, buy the good stuff. It's maybe a little bit more expensive, but in the world of business, time is money, and you're probably going to save yourself a lot of time with these connectors. I guess I didn't explain it very well to you guys, but when we were making our Ethernet connectors, I think I've probably explained it by now, but there was two different sections you were crimping when you use those crimping tools. All right, the first was down here, or right there. All right, and that crimping tool physically pushed that piece of plastic down into the Ethernet cable, so it actually smushed right there. And I told you guys that was grabbing on. You wanted your sheathing, the blue portion on this wire, past that point. So when you crimped it, that crimp there grabbed onto that sheathing, so that way that was providing tension. That way you weren't pulling actually on the electrical. The other portion that you were crimping was actually every one of these little metal connectors. All right. If you look at a side view of these things, with a front view actually, some of them are 2 or 3, but it kind of looks something like that. And when you crimp it, you put your wire right here. And when you crimp it, it pushes all these little pins down into that copper wire. I think it's 3 if you're doing a stranded wire, or it's supposed to be 3 if you're doing stranded wire, and it's 2 if you're doing a solid wire, I think. But yeah, so that crimping tool is actually crimping 9 different things, 8 pins and that little piece of plastic. So, and also, I always find it interesting, but it makes perfect sense. You can't push those connectors in unless you've crimped them. Like you can't put them into a computer or any Ethernet jack unless you've crimped them, because all those little metal contacts are sticking out. So you actually can't put them into something if you haven't crimped them correctly. So that is definitely good to know. This connector is not very rugged. I bet most of you have broken off this stupid tab. Yeah, especially if you're pulling something, that gets caught on the carpet or whatever, and it just bends over backwards on you and then just breaks off right there. You stupid piece of... And what do? Well, you go buy a new Ethernet cable, or you cut the end off, you crimp it on, or you just shove it back in as it sits and hope it doesn't come back out. And again, in most environments, you don't really need that locking tab, right? It's like, okay, I'm plugging this into my laptop temporarily, It's not like I'm carrying my laptop around with this freaking cable plugged in, or hopefully that cable isn't somewhere where someone can trip over it. Although, personally, I'd rather not have the locking tab if someone can trip on the cable, because then it just gets yanked out of the laptop instead of yanking the laptop with it. So, a little bit of give and take. But this is not the most rugged connector in the world. Surprising. Again, for business applications where it's in a server cabinet or plugged into the back of a desktop that's never moving, it is rugged enough. But for an industrial environment, might not be the case. The other thing that you guys might remember is when we were doing the cable testing, we tested and it was pin 1 good, 2 good, 3 good, 4 good, 5 good, 6 good, 7 good, 8 good, and then it was like ground failed. And you guys were like, oh crap, the ground failed. It's like, well, we have a plastic connector. We don't have a metal sheathing in our wire, so there was no way to connect that ground. Right. As you get to different cable types, which we'll talk about in a few minutes, that you will have an extra shielding there, which is grounded, so that way you could actually ground both ends of the connector and whatnot. So, but anyway, so yeah. Not very good. Cat5, UTP, unshielded twisted pair, just a reminder. All right. This is, I'd say though, overall the UTP is the way that most people are going. All right. Again, for business use, it's perfectly fine. For industrial use, maybe going up to the shielding is worth it. It really depends on the environment that your equipment is in. That's what it comes down to. I don't know what the cost difference between them is. So probably it's worth just spending the extra money right off the bat, put the shielding on it, or have the shielding on it and not have to worry about it. But it is something to be aware of. Now, why is the unshielded twisted pair resistant to electromagnetically induced interference? You know what? Remember why? Yeah. We don't have shielding on it, so that's not the reason. But why is this normally pretty resilient against interference? It's the T, twist. By taking those two wires, right, and we do You got that going, and then you've got your other wire doing the exact opposite. Those are, having those twists there are helping reduce that interference. So by having it, so even though it's unshielded, it is still inherently resistant to electromagnetic interference. But it may not still be suited for those industrial environments, because if there's a lot of interference, still could have problems. So something that you do need to worry about in the long run. Now, what are we moving towards? All right. The first one is screened or shielded twisted pair, such as Cat5i. So this is going to have a foil and braid shields for full RF EMI protection. I will show you a picture of that on the next slide. I start looking at this, I'm like, you've got to be freaking kidding me. All right. So it says Cat5i is foil and braid shielded for RF and EMI protection. It's also highly flexible, has a polyurethane jacket. So the actual outside plastic that we have on there, that sheathing, that's a different material, so it's a bit on the stronger side. So that's going to have a longer life in harsh industrial environments. A little bit of give and take going on. It's a wonderful world. You're out there buying something, and you're like, why is that one twice as much as this? Why is that flashlight twice as much as this flashlight? Is it really 2 times as good? Sometimes yes. Sometimes no. You gotta be careful what it comes down to. It's always the case, isn't it? Anyway, optical fiber is another option for those industrial environments. So that is where they're moving for those lots of data, heavy bandwidth things, because again, we can't, basically no interference that can happen in fiber optics. The bigger issue you're going to have is protecting the cable. That's a big benefit. Like I can run this right next to a freaking high power wire and have 0 interference issue. But if you have it on something that's constantly flexing and you've got your radius, like it's flexing to too small a radius or something, then you're going to have problems. So it's always a little bit of give and take going. Up here on the right, that top right picture, that would be our D sub connector. All right. If we actually look at this would be our DB9. You can see there are 9 pins. Yeah. Weird. 1 through 5, and then 6, 7, 8, 9. Got our 5 pins there. So D sub connectors. You may also hear this called the DB connector, as I just said, or the D sub min. So right now, that's kind of one of our go-to connectors. It is oftentimes a really sturdy connector because you've got your little connector sticking out yourself. That's where all those little pins are. And then you've got a metal plate. And as you can see, we've got holes in that plate, so we can actually screw that into something. And then you've got a big plastic housing or something like that. So in that aspect, those D sub connectors are normally pretty sturdy for not getting unplugged. And you can get custom cables that you can just buy these connectors and put them on the end. So you can make a cable however long you need. It's your own personal choice there. We also have the Mini 12 or the M12 form factor. This is governed by the IEC 61076 standard. This is widely accepted for the field bus and automation processes. So that would be this one right here. This is 8 poles. So if we actually look, you can see there's 4 quadrants and 2 pins per quadrant. All right, so we got 8. So we could actually use that for Ethernet. Right? You could say, okay, instead of having this wonderful Ethernet connection right here that I'm going to have, I'm going to run this M12 connector. And it's still got your 8 wires that you can run everything through. So that could be your choice. It all comes down to what type of connector it is that you want to use. This does offer, if you actually can look, we can see that we've got threads on the outside. So just like on the previous slide, or the 2 slides ago, with the RF one where it screws on, this has that same type of connection. So you've got a nice heavy metal jacket. You put your connector together, you screw it together. It's going to be excellent protection against moisture, dust, corrosion, EMI, RFI, vibration, shock, UV radiation, and extreme temperatures. So it does a lot. I'm sure it also costs a pretty penny. Yeah, compared to the like what I think it was like 15 cents for the Ethernet connectors that we're using, maybe that is. But if you look at that, that's a lot of metal. Metal is not. So also to the right of that, we've got a much more heavy-duty Ethernet plug. I'm going to call it. Nothing super special there, but you can see that our little plastic tab that often breaks off is kind of protected. We've got a little like extension clip here that allows you to push on it from a farther location. This probably plugs in a lot deeper. There you can see the grounding that's going on. So we've got that metal grounding on there to provide that. So much heavier duty connection. Not all Ethernet connectors are the same. You can get crazy Ethernet connectors that have like a screw-on socket on the outside. So you would have your standard like Ethernet plug, and it's inside this circle. And so you plug this thing in, and you still have that threaded connection on the outside to actually like pull the thing together. I brought the thing. I should look for this. I have one at home. You can get all sorts of variations that's still just an Ethernet plug. That's all it is. It's an Ethernet. And this Ethernet plug could have two reasons. One, it could be so you have a nice screw-on connection there, or it could have this big screw around it so you can screw a cap on to make it waterproof. When you don't need it, when you need it, you can unscrew and plug out an Ethernet. So it's really a bit of give and take going on here. What's your environment you're working with, and why do you need it, and all those other ones. I like keeping things standard. So like an Ethernet port should have an RJ45 connector. Because that way, if I ever show up somewhere and I'm expecting to plug with my Ethernet cable, but it's got this funky M12 connector, I don't have an Ethernet cable that does that. And then you have to have an Ethernet to M12 adapter, or an RJ45 to M12 adapter for your laptop. Laptop's not going to have an M12 plug on it. So a little bit of give and take. I like to try to keep things as consistent as possible when I can. Go away. So here I have not all, I'm missing one, most of the different types of Cat5 cable. All right, so left to right, top to bottom, the top leftmost one up here, this would be our UTP, our unshielded twisted pair. All right, as you guys were dealing with, right in the center here, there's also that little plastic divider. You guys remember, you guys were kind of cursing that thing, you had to cut it off and cause some problems. So I think that's the difference between 5 and 6. Cat 5, I believe, does not have that little plastic divider in there, where Cat 6 does. It's a slight difference, but it is a difference. Next, you can see we've got that stupid little plastic divider, we've got our twisted pairs, and then we've got foils. So this would be F UTP. So you can see we've got foil. Then next to it we have our shielded UTP. Shielded UTP. Down here, and again, you can see the difference. We've got this coppery, steely, I've got no clue, maybe aluminum. I've got no clue what the braid's made of. But it's a physical braid of wires, where this is just like tinfoil kind of thing. Much thinner, but still basically like tinfoil. Down here we've got SF, so we've got shielded and foiled. UTP, unshielded twisted pair. Shielded with unshielded twisted pair, yep. And then we've got our unshielded with foil twisted pair. And FTP. All right. And notice the difference between this foil and this foil. What is it? Yep. The unshielded foil twisted pair, each twisted set of wires, so two wires together, have their own foil wrapped around them. Where the foiled, unshielded twisted pair, you just have one set of foil around everything. So, not a big difference, but it is a difference. In theory, this one will be better interference from wire to wire, because each one has its own shielding, where this one, wire to wire, you can still get interference. So, a little bit of different take. Next, we've got, what is the foil? Yeah, FTP. So you got FTP. So we've got foil on the outside, And we've got foil on each individual wire set as well. How about you guys? This starts to get a little ridiculous. Then we have shielded with foil twisted pairs. So imagine a combination of these two. All right, so you've got your foil twisted pairs with your shielding around it. I don't have that one. That should be right here. And then we've got our shielded foiled twisted pair. SFTP. Woo! Yeah, it gets a little ridiculous, doesn't it? It's like, how many different freaking grounding protection systems are we putting on these things? I mean, to me, you've got your unshielded twisted pair here, which is already pretty resistant to interference. Then we're going to add foil on each wire. Then we're going to add foil around everything. And then we're going to add a shield on top of that. Holy God. Bit on the ridiculous side, if I may say so myself.
Who's going to use that?
I don't know. Again, anywhere where you have, well, you've got a few options. If you have stupid amounts of interference from whatever industrial application, you're probably going to start with, one and then try to slowly move your way up the scale to find one that is not quite as stupidly interference. So that is, those people would. Maybe if you're in a government situation and you need, shielding, they require whatever the magical spec says. So there's a lot of different options in the long run is what it comes down to. So it's just a matter of what does the code that you're following require, or what does your company require? Other than cost, all of these could be used exactly in the same way. If I want to run an Ethernet cable from my computer to that TV, all of these would work. Some are just a bit more overkill than the other for that situation. Like unshielded, unshielded twisted pair would be 100% fine in this environment. But if you have to run an Ethernet cable next to this big 1,000 horsepower motor that is makes an elevator go up and down or something like that, when that thing turns on and off, better than well believe there's going to be a huge EMI spike right around that. Not only that, but then also for the wires, all the power wires go into it. So, it's like I've got to get to the control panel for that thing, which means I got to get in the room with it. But I'm going to have this giant EMI spike around it from motor turning on, plus all the power wires go into it. They're going to be producing their own EMI because they've got a power voltage drop or whatever. That could just absolutely screw your communications for a few minutes as that thing ramps up. Now, things have also gotten better with VFDs, variable frequency drives. It used to be you want to turn a motor on, it was a contactor closing and that like full power to the motor, like you just flooring your car and spinning those wheels. That caused a huge EMI coming off of it. Now with VFDs, we can do a ramp up. You can actually slowly spin the motor up, so you're not just full powering it. You're kind of feathering the gas in. So it's a much slower process, but it's not creating as much interference. So, VFDs are helping. There's also another device called a soft starter, which is kind of like a middleman between a VFD and a contactor. It doesn't quite have that like frequency where it can completely spin it up from 0 to not full, but it kind of like half speeds it first, so it's not as much just slamming the motor on. So it's softly started. But yeah, so a lot going on when it comes to the world of Ethernet cables. Next slide. There we go. Latency. All right. When we're talking about latency, it's how long does it take for my message to get to you. All right. So whatever that distance. And some, and this says industrial applications, require scan times in the 5 to 20 milliseconds. All right. 5 millisecond scan times or latency requirements. That would be 200 times a second. Think about that. It's running its code 200 times a second. That'd be 5 milliseconds. Or 20 would be what, 50? 500? No, 50. 50 times per second. So that's a huge range. 5 to 20 milliseconds. That's 15 millisecond range, but it's from 200 times a second to 50 times a second. That's a lot of it. It's a huge difference. And my notes say that really demanding processes can require 2 to 5 milliseconds, so even less. So latency is going to be a huge, huge issue. So, for example, on a 10-base-T Ethernet system, the access time on a moderately loaded 100-station network could range from 100 to 10 to 100 milliseconds, which again is fine for office applications. He's saying, "Hey server, I need a copy of this file," and the server's waiting and going, "Oh, okay, here you go," because it's busy doing whatever else. Well, if I have an industrial PLC that's my safety PLC monitoring all the inputs and outputs, you press that e-stop button, you don't want to let it go 100 milliseconds before it's like, "Oh, wait, that person's finger's getting cut off, I should stop the system." No, you hit that e-stop, you want that thing to respond instantaneously. So that's that whole 2 to 5 or 5 to 20 milliseconds. We got to keep that down. So on an industrial network, you might have a 100 megabit network, but we want to keep the utilization down below 10%, normally in the 3 to 4%. And that will help keep our latency times lower. Because okay, it's like my network is designed to have so much throughput of data, yes, but what does that do to your latency? So you want to keep your latency low. To do that, we got to keep our network utilization low. So for commercial Ethernets, 25-30% is kind of what they're acceptable. For industrial, as I said, less than 10. Normally, ideally, like 3 to 4. Now, with the advent of faster gigabit networking, this has become less of an issue. All right. It's still a problem. We still don't want to have too much utilization and too much latency. By having so much more throughput of data and how much quicker we can send information, the latency is, we can now have more stuff happening on the network and still have low latency. So a little bit of give. You have to remember that routers and switches and things, they're sending packets of data, like sending you a message via the mail. And if we all say, "Hey, I need this information," you all throw your mail into the mailbox at the same time. There's only one mail carrier, only one cable going that route. You can't send 10 messages at once. Only one message can send at a time. Since you're sending so many bits of information, by doing it on 1,000 meg versus 100 meg, going 10 times faster. In theory, our utilization and whatnot should be able to be 10. So that is helping. Also, VLAN technology, the virtual local area networks, where we can now start saying, "Okay, I'm going to group you together and you together," so that way all of your information doesn't get over here where they don't give a damn about it. We're able to. That keeps their network utilization lower, so that way they're able to communicate faster. The IT world having moved up a lot in technology with LANs and ultra LANs and all the other wonderful things and higher speed networking, that has caused greater capability for our industrial network. Less networking. Big benefit there. However, we do have some issues with the Ethernet size of the Ethernet frame. Ethernet frame is 60 bytes that you're transmitting of data. Right? So and this is part of latency. If you're only trying to send 2 bytes of data, DINT or an int or whatever it is, 60 bits. You're like, all you need to tell them is that this button's been pressed. You're trying to send it out on the network. That's one freaking bit of information. You still have to send 60 bytes of information over. 60 times 8 is 480 bits. So to send 1 bit, button's been pressed, I am sending 480 over the Ethernet. All right, so that's why latency can be a problem in the world of Ethernet. Now, as I said, with 100 megabits or gigabits with full duplex, that is becoming less of an issue. It's still something that you want to try to group things like that you can when possible. It's kind of funny to me in the Allen Bradley software, you cannot share a Boolean with another PLC. If you have 2 PLCs on a network and you want to send information between them, you can't send a Boolean, which is 0 or 1. You have to share a DINT. I think it's an int. Anyway, you have to send like 16 bits. Even if you only care about sending one of those bits, you have to send the whole 16. And it's just how the game works. Right? information, it's all 16. So you have to save your variables right. And yeah, you could say, okay, this is push button 1, but it's a dint. Like I'm only using push button 1.0. This is push button 2.0. This is push button 3.0. Or you could just say push buttons, and .0 would be the push button first one, and .1 would be the second one, and .2 would be the third one. So I'm sending the same amount of information, but I'm only sending one variable of data back and forth. You can greatly reduce your communications by just having a better protocol for transmitting back and forth. A lot going on there. Also, another benefit to VLANs, which would be our network partitioning, is security. Security is a huge issue in the industrial world nowadays. We've kind of talked about this before, but old equipment, when they designed it, they didn't know that the internet was going to be this big and everything was going to be connected to it. So it wasn't a huge problem. But now that we're putting these old devices on the network, and it's devices that were never expected to be put on the network, that security has become a problem, because it's like, oh, if I plug in this Ethernet jack and you're connected from the business network to the industrial network, I can now talk to every one of your PLCs, which I've done here. I don't know what PLCs I was talking to. I think it's those on that robot. I don't know why. They shouldn't be on the network. One day I did a scan of our network from the STEM building, and all of a sudden there's like 5 or 6 PLCs showing up that I was not expecting. What the hell are these things? And it's just like, hey, our purposes of HCC, it wasn't a problem because it was training people, I think. But like in the industrial world, you don't want the admin assistant who sits at the front desk talking to everybody and opening doors and answering questions, going on a bathroom break and have some stranger walk in, sit down at their desk and be able to talk to your PLCs and then industrial network next. That's a huge security, because if I do that, it's like, let me change the preset temperature. If I go up to this, it's going to melt something. It's going to ruin their entire batch, and that's thousands of dollars out the window that company costs. So you don't want those types of things. So we need to do lots of security now. So by network partitioning or VLANing, we're doing security, we're doing speed response times. So that is awesome. The other thing is switches versus hubs. Right? Any of you guys, said doing a little home networking at home, you may have seen a device that looks just like this. Just, like 4 ports, or 8 ports, or 10 ports, or 25 ports. Right? And you may see one that looks just like it, right next to it. And they could be the exact same thing. These are all Ethernet ports. All right? Or you could be at Best Buy and you're going, what the hell is the difference between these two? You're looking at 2 boxes. Like, they look exactly the same. And one says it's a switch, and one says it's a hub. You're like, they look the same. Why is the hub $10 cheaper or whatever? And you're like, screw it, I'm going to buy the hub. I'm going to save $10. All right? The hub is dumb, is what it comes to. Where a switch has some smarts built. So to reduce latency, you need switches. You can't have hubs. And how they reduce latency is every time a hub gets a message, you send your request to the server in this port, it sends it out every one of these ports. It's just like broadcasting to the whole world. Hey, I need server information. And my device gets it, and Tim's device gets it, and Milborn's, and Cam, and everyone gets that information. And none of us are the servers who are like, all right, I don't care, you just ignore the message. But that was still a message you had to receive, which meant it was transmitted on your wire, which was meant processing time was taken up. Or a switch, on the other hand, gets that same exact message, and it just goes, oh, the server's out this way. So it just sends that request out that same. So that reduces information and whatnot being transmitted. So anytime you can, buy a switch, not a hub. Right? Spend the extra few bucks. Home use. So it will do you that instance. All right. Back to the OSI, the application layer. That was the very top layer. Right? Unluckily, there are special application layers, yes, plural purpose there. Right? My notes, as they're saying, is industrial vendors will implement their own special application layer. My application layer, as Alan Bradley, might be different than Siemens, might be different than Click, might be different from B, and it starts to become stupid freaking. And nice thing is, they're all still based on Ethernet, so they can all still be plugged in the same network. But they all may be on the same network, they're getting the same IP address ranges, types of things, but they can't talk to each other because of that different application. And it's, again, that world of one of two things. Either world one is we want everyone to have to buy our equipment, so we're not going to be nice and talk to each other. Or world two of, well, our standard's better than yours, so everybody should use our standard, and then everyone will be able to talk. But they all think that. By all thinking that, it doesn't do any good. So it's a little bit of give and take going on in that aspect of things. Yeah, it just sucks when it comes. And then we have MMS, which some of you who are really into their cell phones might have heard of that as multimedia messaging. All right. However, in the world of industrial, that is the manufacturing messaging service. So it's still messaging, it's just manufacturing. This is a protocol that was developed that has been promoted as truly open, I'm going to put that in quotes, automation application layer protocols, but with limited acceptance. Someone came up with this and said, hey, everybody, you should use it. This is why it's really good. We'll all be able to talk to each other, yada, yada, yada. And all the companies were like, screw you. I mean, that's how I look at this, at least. No, we're not actually going to follow that. Yeah, a little bit of give and take. It's a slow process. I have a love-hate relationship with open source. I'm going to leave it there. So open source is great, but it can cause problems. So, all right, so the industrial Ethernet protocols. We have standard software, standard Ethernet, open software, standard Ethernet, and open software, modified Ethernet. The biscuit, they all look the same, right? So, standard software, standards Ethernet. This uses Ethernet with the TCP IP, so just like we would use with, my computer right here. And this adds mechanisms built into the application layer to enable that real-time communication. Right. Remember, we were talking about industrial networks sometimes needing sub 5 millisecond response time. So if we need real time and we're relying on Ethernet, it's not necessarily going to be real time. Maybe you guys have been running a ping test. Sometimes it doesn't go very quickly. So something that we need to be aware of. And this is what Ethernet IP is based on, this architecture. Open software, standard Ethernet. This uses your standard Ethernet layers with new standard protocols that manage access to the network. So, kind of standardy, but not quite. This allows synchronization of the data being sent from each node to ensure priority data is sent first. So, you can add like a priority level and say, hold up, stop sending your data, I'm more important. And the switch is like, oh yeah, okay, and it shoots that message off first, and then it can use whatever has been queued up right behind. So that allows us to get down to those sub 2 milliseconds. This is Ethernet PowerLink uses this architecture. And then we have open software modified Ethernet, and this is based on standard Ethernet hardware. It uses new protocols and additional complementary hardware to ensure determinism. This is what EtherCAT, Circos 3, Profinet IRT use, but they do so with different hardware and transport mechanisms. Back to the whole wonderful world of things being open. It's like, well, it's open, but I can modify the open. Yes. I'm going to use your stuff, but not use your stuff. I'm going to take what I like and not what I don't like, which is wonderful as long as they're distributing what they've changed so that other people can use it. Oftentimes there is open source hard software. They get into programming. The licensing is like, you may use our open source hardware or software. You may change our open source software, but you must distribute your changes. So it's like, you want to use all our hard work? That's fine. But whatever you modify, you have to publicize, so if other people want to use it, then they can use it. So little bit of give and take going on there. All right, and here we have the OSI model for Ethernet IP. All right, this is on Ethernet IP is the industrial protocol. So you can see that we've got the CIP is the top 3 layers, TCP/IP is still 4 and 3, and Ethernet is still 1 and 2. And again, still still got your MAC address, you still got your physical Ethernet. So a lot going on there. All right, and then my last slide that I've got for this PowerPoint today. Some examples that you might see. We might see Ethernet IP. IP, as I said, is industrial protocol. This performs at levels 5, 6, and 7 of the OSI. The CIP, the Common Industrial Protocol, that CIP, that's those top 3 layers. Ethernet packets used with this protocol of CIP, TCP/IP, or UDP layers to provide the required data to your controller. So kind of pick what we want to be transmitting information on. This does promote consistent implementation of automation functions across a diverse ecosystem of products. So again, this is trying to bring multiple vendors' information, everything together, so that way you can actually talk between vendor A and vendor B. Big benefit there. We also have Profinet, which, as I've told you guys, is Alan Bradley's Ethernet communication. Father's living daylights out of me. Let's just stop this prior to But again, if Ethernet doesn't fit your needs because of time restraints or whatever the case is, you got to adapt. That's how they adapt. Then you have Modbus/TCP. So we'll talk about Modbus another day. And then you also have Fieldbus, which is another one that we should be talking about another day as well. There is a lot going on in the industrial. And on the right here, I just got a little picture of what is kind of going on. So at the bottom here, from this point down, this is our industrial network, and then this is our corporate network. We've got HMI, for this would be embedded right into a machine somewhere. You've got your PC-based HMIs. We've got our PLCs, our motors, drives. We got robots. Those are some really funky-looking robots. I don't know what those are. But you can see how we've got firewalls and managed switches here, so that's helping to protect the industrial network. You also do notice, hopefully, that we've got this triangle going on. A love triangle. Not that little. All right. So if one link goes down, there is still communication path opportunity. The world of networking, unluckily, is without redundancy. So when things break, not if, but when, your whole network doesn't just come crashing and burning. Okay. Luckily for us, for personal use at home, if you lose your internet for a few hours, it's a crappy day, but it's not the end. In the industrial world, you lose your internet or a network link or whatever, you can be out thousands of dollars because all of a sudden you can't access the right server or whatever the case is. Redundancy is going to be key here. All the communication actually. That's what's going on with that one. All right, any major questions for me before we move on?
Profinet.
Yep. That's just Allen Bradley's. Siemens is Ethernet communication. Most modern PLCs, they come with Ethernet built. It used to be if you wanted to program a PLC, it was over serial. Actually, it would have a DB9 connector on there somewhere. And like on Allen Bradley's, I actually have an example of this. Right. Oh. I didn't do it. No picture. What the heck did I do? That's a new one. Oh, okay. Must have been that kick the HDMI. And of course, I don't have a picture on that either. Well, that's great. All right. Well, anyway, on Allen Bradley PLCs, there is a little circular port. In this case, it's embedded like right here. There's a little cover that goes over it. There's a place for a cable to come out, but that is our communication port for this PLC. So It used to be if you want to program this, you had to have the special cable that would reach all the way down in there and plug in into serial. They did actually have little adapters, so you could plug in there and put that on the network. But that was how they did it. Profinet is actually an evolution from Profibus, which again is Siemens Communications. So it's just, they've kind of modified it. Oftentimes, a lot of these industrial protocols are modifying serial communication to the Ethernet standard to some way. So that way, it's like, well, we had to change basically the cable, the media, how we're connected, but most of the protocols that are actually being sent and messages and things haven't changed. It's more of just, we're going from serial to Ethernet. We're using that hardware for the Ethernet, but we're still using the same types of messages. Alrighty.